Have you ever looked up at the night sky and wondered how long this cosmic dance will continue? Our sun rising faithfully each morning, the planets spinning in their eternal orbits, the delicate balance that keeps our little corner of the universe humming along so perfectly. It's easy to assume this celestial clockwork will tick forever, but here's something that might surprise you. Our solar system has an expiration date. Tonight we're embarking on a journey through deep time, exploring the slow but inevitable transformation of everything we know. From the gradual brightening of our sun to the spectacular death throes that await billions of years in the future, we'll uncover the fascinating timeline of how our solar system will meet its end. And trust me, the story is far more complex and surprising than you might expect. Before we dive into this cosmic tale, I'd love to know where you're watching from tonight and what draws you to these mysteries of the universe. There's something profoundly humbling about contemplating such vast stretches of time, isn't there? If you find these explorations through space and time as captivating as I do, a gentle tap of that like button would mean the world to me, and perhaps consider subscribing for more journeys into the wonders of our cosmos. Now, settle in and let your imagination stretch across eons, because we're about to witness the biography of a solar system, from its current middle age all the way to its final chapter. The universe has written quite a story for us, and it's time to turn the pages. Our solar system's death isn't a single event, but rather a slow, intricate process that will unfold across timescales so vast they challenge our very ability to comprehend them. When we talk about the end of our cosmic neighborhood, we're not discussing something that happens overnight or even over millions of years. We're venturing into billions and trillions of years, timeframes that make the entire history of human civilization look like the blink of an eye. The curious thing about our solar system's demise is that it begins not with violence or sudden catastrophe, but with something as gentle as a gradual increase in brightness. Our sun, that steady companion that has nurtured life on Earth for billions of years, is slowly but inexorably growing more luminous. This isn't some distant threat lurking in the far future. It's happening right now, moment by moment, as nuclear fusion in the sun's core converts hydrogen to helium with ever-increasing efficiency. Over the past 4.5 billion years, our sun has already grown about 30% brighter than when it first ignited. That might not sound particularly alarming, but consider this. Over the next billion years, it will grow another 10% brighter still. This seemingly modest increase carries profound implications for every world in our solar system, particularly our own. As the sun's luminosity increases, Earth will begin to experience what scientists call a runaway greenhouse effect. The additional heat will start melting the polar ice caps more rapidly, sending vast quantities of water vapor into our atmosphere. Water vapor, as it happens, is an excellent greenhouse gas, far more effective at trapping heat than carbon dioxide. This creates a feedback loop where more heat leads to more water vapor, which traps even more heat, which creates even more water vapor. The transformation will be gradual at first, almost imperceptible on human timescales. But as the centuries roll by, the effects will compound. The ice caps will shrink year after year. Ocean levels will rise not just from melting ice, but from thermal expansion as the seas grow warmer. Coastal regions will disappear beneath the waves. Weather patterns that have remained relatively stable for millennia will shift and intensify. Within roughly 1 billion years, this process will reach a tipping point. The oceans themselves will begin to boil away. The protective blanket of our atmosphere will be stripped away by increasingly powerful solar winds. Earth will transform from the blue marble we know today into something resembling Venus, a scorched, lifeless world shrouded in crushing heat and toxic gases. But here's where the story becomes particularly fascinating. While Earth faces this slow-motion catastrophe, other worlds in our solar system will experience the opposite effect. The outer planets and their moons, currently frozen in perpetual winter, will begin to thaw. Jupiter's moon, Europa, with its subsurface ocean locked beneath miles of ice, may finally feel warmth on its surface. Saturn's moon Titan, already possessing a thick atmosphere, could develop conditions remarkably similar to early Earth. This gradual brightening represents just the opening act of our solar system's transformation. The Sun is currently what astronomers call a main sequence star, steadily burning hydrogen in its core and maintaining a relatively stable size and temperature. But like all stars, it carries within itself the seeds of its own dramatic metamorphosis. The nuclear fusion process that powers our Sun is gradually changing its internal composition. With each passing moment, hydrogen atoms in the core are being converted to helium. Helium is denser than hydrogen, so as more helium accumulates in the Sun's center, the core becomes more compact and the fusion process becomes more efficient. This increased efficiency is precisely what's driving the gradual increase in brightness we discussed earlier. But this process can't continue indefinitely. Eventually, roughly 5 billion years from now, the hydrogen fuel at the Sun's core will be exhausted. When that happens, fusion in the core will cease and the Sun will face an energy crisis. The outward pressure from nuclear fusion, which has kept the Sun's massive bulk from collapsing under its own gravity for billions of years, will suddenly be gone. What happens next is one of the most spectacular transformations in the cosmos. The Sun's core, no longer supported by fusion pressure, will begin to contract under its own immense gravitational pull. As it contracts, it will heat up dramatically. This heating will ignite a shell of hydrogen surrounding the now inert core, creating a new source of energy that burns far more fiercely than the original core fusion. The energy from this shell burning will cause the Sun's outer layers to expand dramatically. Over the course of just a few million years, our familiar yellow Sun will transform into a red giant, a bloated stellar behemoth whose surface may extend all the way to Earth's current orbit. This expansion will be swift on astronomical timescales, but still gradual enough that we could watch it unfold if we were somehow present to witness it. The Sun's surface will cool as it expands, giving it a reddish hue, but its total energy output will increase dramatically. The habitable zone, that narrow band around a star where liquid water can exist on a planet's surface, will shift dramatically outward. Mercury, the innermost planet, will be the first casualty of this expansion. The expanding solar atmosphere will engulf it completely, and the tiny world will spiral inward through the increasingly dense solar material. Friction with this material will cause Mercury to lose orbital energy, and it will eventually be consumed entirely by its parent star. Venus will meet a similar fate, though it may last slightly longer due to its greater distance from the Sun. The thick, toxic atmosphere that currently makes Venus a hellish greenhouse world will be stripped away entirely by the intense radiation and stellar winds from the red giant Sun. Earth's fate during this period remains a subject of scientific debate. Some models suggest that our planet will be engulfed along with Mercury and Venus. Others propose that the Sun's mass loss during its red giant phase will cause Earth's orbit to spiral outward, potentially allowing it to escape destruction. However, even if Earth physically survives the Sun's expansion, it will be subjected to temperatures hot enough to vaporize rock. Any remnant of our once blue world would be reduced to a lifeless, molten sphere. The outer solar system will experience this period very differently. Mars, currently a cold desert world, will briefly enjoy more temperate conditions. The asteroid belt will be bathed in warmth it has never known. Jupiter and Saturn, those gas giant guardians of the outer system, will face a complex fate. The intense radiation from the red giant Sun will initially strip away portions of their atmospheres. But as the Sun continues to expand and shed material, some of this stellar matter may actually be captured by the giant planets, causing them to grow larger than they've ever been. The moons of the outer planets will undergo their own remarkable transformations. Europa's icy shell will melt completely, potentially creating a global ocean beneath a steamy atmosphere. Enceladus, currently known for its geysers of water ice, may develop conditions suitable for liquid water on its surface. Titan, with its thick atmosphere and hydrocarbon lakes, might experience a brief golden age where liquid water oceans exist alongside its existing methane seas. This red giant phase will last for approximately 1 billion years, a period longer than complex life has existed on Earth. During this time, the sun will pulsate and vary in brightness, shedding material in powerful stellar winds. These winds will carry away a significant portion of the sun's mass, perhaps as much as half of its original bulk. The material shed during this phase won't simply disappear. It will form expanding shells of gas and dust around the dying star, creating one of the most beautiful phenomena in the universe, a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. They earned this designation because early astronomers thought their round, disc-like appearance resembled planets when viewed through primitive telescopes. These nebulae represent the sun's final gift to the cosmos. The heavy elements forged in the sun's core over billions of years, including the carbon, nitrogen, and oxygen that are essential for life as we know it, will be scattered into space. This material will eventually be incorporated into new stars and planetary systems, ensuring that the atoms that once comprised our world will continue their cosmic journey long after our solar system has ceased to exist. As the red giant phase draws to a close, the sun will experience its final dramatic transformation. The helium that has been accumulating in its core will finally ignite in a process called the helium flash. This event will be brief but incredibly energetic, causing the sun to pulse and shed even more material. The outer layers of the star will be expelled entirely, leaving behind only the hot, dense core. This remnant core will become what astronomers call a white dwarf, a star roughly the size of Earth but containing most of the sun's original mass. White dwarfs are incredibly dense objects, with a teaspoon of white dwarf material weighing as much as a car. They shine not from nuclear fusion, which has permanently ceased, but from the residual heat left over from their formation. The white dwarf that was once our sun will be blindingly hot when it first forms, with a surface temperature of perhaps 100,000 degrees Celsius. However, with no internal source of energy, it will begin cooling immediately. This cooling process is extraordinarily slow, taking billions of years for the white dwarf to fade to a more modest temperature. This new phase of our solar system's existence will be radically different from anything we can imagine today. The white dwarf sun will be much smaller and dimmer than our current star, creating a new habitable zone much closer to its surface. Any planets that survive the red giant phase will find themselves in a completely transformed environment. The surviving outer planets, Jupiter and Saturn, will continue their stately orbits around this stellar remnant. Their orbital periods will change as the sun's reduced mass weakens its gravitational hold on them, but they should remain stable for billions of years to come. They will be lit not by the warm yellow light we associate with our sun, but by the harsh blue-white glare of the white dwarf. But even this phase is not the end of our solar system story. The white dwarf will continue to cool and fade over trillions of years, eventually becoming a cold, dark object called a black dwarf. During this unimaginably long period, other forces will come into play that will ultimately determine the final fate of any remaining worlds in our system. The gentle cooling of our white dwarf sun marks the beginning of an era so long that it dwarfs everything we've discussed so far. While the transformation from main sequence star to white dwarf unfolds over mere billions of years, the cooling phase stretches across timescales that challenge the very meaning of forever. We're entering a period where the familiar rhythms of planetary motion will persist, but against a backdrop of cosmic loneliness that's difficult to fathom. During these trillion-year epochs, our solar system will face threats that have nothing to do with stellar evolution. Space, you see, is not the empty void we often imagine it to be. Our sun, along with its retinue of planets, is constantly moving through the galaxy, orbiting the center of the Milky Way roughly once every 230 million years. This galactic journey brings us into contact with other stellar systems, and occasionally these encounters can be disturbingly close. Imagine, if you will, another star approaching our solar system, not close enough to see with the naked eye during a human lifetime, but close enough that its gravitational influence begins to tug at the delicate orbital mechanics that have kept our planets in their predictable paths for billions of years. These stellar flybys occur more frequently than you might expect. On average, a star passes within about 10,000 astronomical units of our Sun every 20 million years or so. Most of these encounters are gentle affairs, causing only minor perturbations in planetary orbits. But statistics tell us that much closer approaches are inevitable, given enough time. Every billion years or so, a star wanders within 1,000 astronomical units of our system. Every 100 billion years, one passes within just 100 astronomical units. To put that in perspective, that's roughly twice the distance from the Sun to Pluto. These close encounters don't just disturb the planets themselves. Far beyond the orbit of Neptune lies a spherical shell of icy bodies called the Oort cloud, containing perhaps 1 trillion comets in a slow dance around our Sun. When a passing star gravitationally stirs this distant reservoir, it can send showers of comets tumbling toward the inner solar system. If any worlds still harbour life during these far future epochs, these comet storms could trigger mass extinction events that make the asteroid impact that killed the dinosaurs look like a gentle spring rain. But the real drama of these stellar encounters unfolds over even longer timescales. Computer simulations that follow the evolution of our solar system across 1 trillion years reveal a sobering truth. Eventually, these gravitational nudges will begin to destabilize the orbits of the planets themselves. It's a slow process, like water gradually wearing away stone, but the outcome is inexorable. The first planets to be affected will likely be the smaller worlds with weaker gravitational holds on their parent star. Mars, if it survives the Sun's red giant phase, might be the first to feel the cumulative effects of countless stellar encounters. Its orbit could gradually become more eccentric, more elliptical, until one day it swings too close to Jupiter or too far from the Sun and finds itself ejected from the solar system entirely, doomed to wander the cold depths of interstellar space as a rogue planet. Earth, assuming it somehow survives as a charred remnant orbiting the white dwarf Sun, faces a similarly uncertain future. The gravitational dance between the planets, so stable on the timescales we're familiar with, becomes chaotic when viewed across billions of years. There's less than a 1% chance that Earth will collide with another planet during the Sun's red giant phase, but over the vast stretches of time we're discussing, even unlikely events become inevitable. The outer giants, Jupiter and Saturn, will be the last planets standing in this cosmic game of musical chairs. Their massive size and distant orbits make them more resilient to the gentle gravitational nudges from passing stars. But even they are not immune to the slow erosion of deep time. Eventually, perhaps 50 billion years after the Sun becomes a white dwarf, one of these giants will receive just the right gravitational kick from a passing star to break free from the solar system forever. Picture Jupiter, that massive guardian that has protected the inner solar system from countless asteroid impacts throughout Earth's history, slowly drifting away from the fading remnant of our Sun. Its orbital speed gradually increases with each stellar encounter until finally it reaches escape velocity and begins its lonely journey through the galaxy. Any moons still orbiting Jupiter will accompany it on this exodus, creating a miniature planetary system adrift in the cosmic dark. This process of planetary ejection isn't unique to our solar system. Astronomers estimate that there may be more rogue planets wandering the galaxy than there are stars. These orphaned worlds, cast out from their birth systems by gravitational interactions, drift through space, carrying with them the story of their origins. In the far future, our own planets may join this lonely population of cosmic wanderers. But stellar encounters aren't the only force reshaping our solar system's distant future. Our entire galaxy is on a collision course with its nearest large neighbour, the Andromeda Galaxy. This cosmic smash-up, predicted to occur in roughly 4.5 billion years, will happen during the late stages of our Sun's main sequence lifetime, just as it's beginning to show signs of the brightening that will eventually lead to its red giant phase. The prospect of a galactic collision sounds catastrophic, but the reality is far more subtle. Galaxies are mostly empty space, and the chances of any individual star actually colliding with another during this merger are vanishingly small. Instead, the gravitational interactions between billions of stars will reshape both galaxies, creating a single, larger elliptical galaxy that astronomers have playfully dubbed Milkomeda. For our solar system, this galactic reshuffling could have profound consequences. There's roughly a 50% chance that we'll be flung much farther from the galactic center than we are today, out into the sparse outer regions where stars are few and far between. There's also about a 12% chance that our entire solar system will be ejected from the merged galaxy altogether, cast out into the void between galaxies. Being ejected from the galaxy might sound like a death sentence, but it would actually have little immediate effect on our solar system. The sun would continue to shine, the planets would continue their orbits, and if any life somehow persisted on the outer moons during the red giant phase, it could theoretically continue to exist. The main difference would be the night sky, which would no longer show the familiar band of the Milky Way, but instead display the merged Milkomeda galaxy as a distant island of light in an otherwise empty cosmos. Recent observations have added an intriguing twist to this story. When astronomers factor in the gravitational influences of nearby galaxies like the Large Magellanic Cloud, the certainty of the Milky Way-Andromeda collision becomes much less clear. There may be only a 50% chance that the collision will occur at all over the next 10 billion years. The universe, it seems, still has surprises in store even for our most distant future. As we venture further into deep time, the very nature of matter itself comes under scrutiny. Some theoretical physicists propose that protons, the building blocks of atomic nuclei, may not be stable over truly cosmic timescales. If protons do decay, they would do so with a half-life measured not in billions or trillions of years, but in numbers so large they require scientific notation even to write down. We're talking about 10 to the 34th power years, possibly much longer. To put this in perspective, if proton decay occurs at all, it would represent the ultimate end not just of our solar system, but of all normal matter in the universe. Planets, stars, asteroids, comets, everything we think of as solid and permanent would gradually dissolve into subatomic particles and energy. The process would be so slow that it would make the cooling of white dwarf stars look like a brief moment. But given infinite time, even the most stable structures would eventually succumb. But perhaps we're getting ahead of ourselves. Long before protons have a chance to decay, our solar system will have been reshaped by forces much closer to home. The chaotic nature of orbital mechanics means that even without external influences from passing stars or galactic collisions, the solar system's configuration is not guaranteed to remain stable over billions of years. The gravitational interactions between planets, while small, accumulate over time in ways that can lead to dramatic changes. Computer models suggest that there's a small but measurable chance that Mercury's orbit could become so elongated that it either crashes into the Sun or gets ejected from the solar system entirely. Venus could potentially collide with Earth, or Mars could be scattered outward to join the asteroid belt. These scenarios remain highly unlikely on any timescale humans can relate to. But when we're discussing the lifetime of stars and the evolution of galaxies, even unlikely events become part of the story. The solar system we see today, with its orderly arrangement of planets in stable, nearly circular orbits, represents just one moment in a much longer tale of gradual change and occasional chaos. There's something both humbling and oddly comforting about contemplating these vast stretches of future time. The challenges facing our solar system billions of years from now are so far removed from anything we can directly experience that they take on an almost abstract quality, like equations in a physics textbook rather than real events that will someday unfold. Yet these future chapters in our cosmic story remind us that change is the only constant in the universe. The solar system that nurtured the evolution of life on Earth, that provided the stable conditions necessary for consciousness to emerge and contemplate its own origins, is itself temporary. Like everything else in the cosmos, It carries within itself the seeds of its own transformation. As we drift deeper into these contemplations of deep time, there's a curious paradox at work. The more we learn about the ultimate fate of our solar system, the more precious our current moment becomes. We exist during a brief, miraculous interval when conditions are just right for complexity and beauty to flourish. The very fact that we can understand and appreciate these cosmic cycles is itself a kind of miracle, a temporary arrangement of matter and energy that has somehow achieved the ability to contemplate its own existence. In the meantime, while our solar system navigates these cosmic uncertainties, there are more immediate stellar neighbours that pose their own unique threats. Astronomers have identified several stars on trajectories that will bring them uncomfortably close to our solar system over the next few million years. One such visitor, a red dwarf star called Gliese 710, is currently racing toward us at about 14 kilometers per second and will make its closest approach in roughly 1.3 million years. When Gliese 710 arrives, it won't come close enough to directly disturb the planets, but it will dive deep into the Oort cloud, that vast spherical shell of comets that surrounds our solar system like a gossamer bubble. The gravitational disruption could send millions of these icy wanderers tumbling toward the inner solar system, creating a comet shower that could last for millions of years. Any civilizations that might exist at that time would witness spectacular displays in the night sky, but they'd also face an increased risk of impacts that could reshape the surfaces of worlds and alter the course of biological evolution. These stellar encounters follow a rhythm all their own. On average, a star passes within the general vicinity of our solar system every few 100,000 years. Most are distant enough to cause only minor perturbations, like a gentle breeze rippling the surface of a pond. But occasionally, perhaps once every few million years, a star approaches close enough to leave a lasting mark on our cosmic neighbourhood. The effects of these encounters cascade through the solar system in ways both subtle and profound. A slight gravitational tug on Neptune might alter its orbit by just a few thousand kilometers. But over millions of years, that tiny change propagates through gravitational resonances with other planets. Uranus might shift slightly, which influences Saturn, which in turn affects Jupiter, and so on down the line until even the inner rocky planets feel the ripple effects of that distant stellar flyby. It's a bit like a cosmic version of the butterfly effect, where small changes accumulate into large consequences over vast periods of time. The solar system we observe today carries within its orbital architecture the subtle signatures of countless stellar encounters from the deep past, and it will continue to be sculpted by such meetings long into the future. But perhaps the most fascinating aspect of our solar system's far future involves the possibility of new worlds being born, even as others are dying. During the red giant phase, when the sun sheds enormous amounts of material into space, some of this stellar matter won't escape the solar system entirely. Instead, it may collect in distant regions where it could condense into new celestial bodies. These wouldn't be planets in the traditional sense, but rather strange hybrid objects formed from the cooling gases of a dying star. They might resemble brown dwarfs, those failed stars that never quite managed to ignite nuclear fusion. Or they could form entirely new categories of objects that don't exist anywhere in the universe today. The outer solar system during the red giant phase could become a stellar nursery of sorts, giving birth to exotic new worlds even as the familiar planets of our youth face destruction. The surviving gas giants, Jupiter and Saturn, will play crucial roles in this process. Their immense gravitational fields will act like cosmic vacuum cleaners, sweeping up the expanding solar atmosphere and growing larger than they've ever been. Jupiter could potentially double or even triple its current mass, transforming into something approaching a brown dwarf itself. Saturn, with its delicate ring system, will face a more complex fate as the intense radiation from the red giant sun vaporizes its icy rings, but it too may grow substantially by accreting stellar material. This period of growth and transformation will be relatively brief on astronomical timescales, lasting only as long as the sun remains in its red giant phase. Once the outer layers are shed and the white dwarf is revealed, the supply of new material will cease and the solar system will settle into its new configuration. But the changes wrought during this chaotic interlude will define the character of our system for billions of years to come. The white dwarf phase brings its own peculiar challenges and opportunities. These stellar remnants are notorious for their intense magnetic fields and occasional outbursts of radiation. If any material falls onto the surface of a white dwarf, perhaps from a passing comet or asteroid, it can trigger a thermonuclear explosion called a nova. These events can briefly make the white dwarf shine thousands of times brighter than normal, bathing any surviving worlds in intense radiation. For planets orbiting close enough to the white dwarf to be in its new, much smaller habitable zone, these nova events could be catastrophic. Any atmospheres would be stripped away and surface conditions would become hostile to life as we know it. Yet there's also a strange beauty in these stellar tantrums as they illuminate the surrounding space with brilliant flashes of light that can be seen from vast distances across the galaxy. The very concept of a habitable zone around a white dwarf opens up intriguing possibilities that stretch the imagination. These zones would be incredibly close to the stellar remnant, much closer than Mercury orbits our current Sun. Any planet existing in such a location would be tidally locked, with one hemisphere permanently facing the white dwarf in eternal day, while the other remains shrouded in perpetual night. The day side of such a world would be scorched by the intense blue-white radiation of the white dwarf, while the night side would be frozen in permanent darkness. But along the terminator, that boundary between day and night, there might exist a narrow band where temperatures are just right for liquid water to exist. It would be a twilight world lit by the eternal sunset glow of a dying star, where any remaining life would huddle in the narrow zone between fire and ice. Scientists have already discovered planets orbiting white dwarf stars elsewhere in the galaxy, proving that worlds can indeed survive their star's transformation and continue to orbit the stellar remnant. These discoveries provide a glimpse into our own solar system's potential future, suggesting that the story doesn't necessarily end with the Sun's death, but might continue in forms we're only beginning to imagine. The physics of these white dwarf planetary systems are unlike anything we see in our current solar system. The extreme gravitational field of the white dwarf creates tidal forces that could tear apart any object that ventures too close. Rocky planets might be stretched and compressed until they break apart, forming rings of debris around the stellar remnant. Larger objects might survive intact, but would experience constant seismic activity as the tidal forces knead their interiors like cosmic hands working bread dough. Yet even in this harsh environment, there's potential for unexpected beauty and complexity. The debris rings formed from destroyed planets could create spectacular light shows as material spirals inward toward the white dwarf. The intense radiation field could drive chemical reactions in ways that don't occur anywhere else in the universe, potentially creating exotic compounds and crystalline structures that exist nowhere else. As we venture even further into deep time, beyond the white dwarf phase, and into eras measured in hundreds of billions of years, the very notion of what constitutes our solar system begins to blur. The gravitational sphere of influence that defines where our sun's dominion ends and interstellar space begins will shrink as the white dwarf continues to lose mass through stellar winds and radiation. Objects that are currently considered part of our solar system, like comets in the distant Oort cloud, may gradually drift away as the weakening gravitational grip of the white dwarf can no longer hold them. Our solar system will slowly evaporate, not through any dramatic event, but through the gentle erosion of deep time and the inexorable weakening of gravitational bonds. The asteroid belt, that collection of rocky debris between Mars and Jupiter, will face its own uncertain future. Some asteroids may be captured by the surviving gas giants, becoming new moons in their expanded satellite systems. Others might be perturbed into planet-crossing orbits, leading to spectacular impacts that reshape whatever worlds remain. Still others could be ejected from the system entirely, joining the population of interstellar wanderers that drift through the galaxy. Even the fundamental forces that govern planetary motion will subtly change over these vast timescales. Einstein's theory of general relativity predicts that orbiting objects lose energy by radiating gravitational waves, causing their orbits to slowly decay. This effect is negligible for planets orbiting normal stars, but around the ultra-dense white dwarf, it becomes more significant over billions of years. The closest surviving planet to the white dwarf would be the first to feel this effect, gradually spiraling inward as it loses orbital energy to gravitational radiation. The process would be almost imperceptibly slow at first, but it would accelerate as the planet moved closer to the stellar remnant. Eventually, the planet would cross within the white dwarf's Roche limit, where tidal forces overcome the planet's self-gravity, and it would be torn apart to form a ring of debris. This cosmic dance of orbital decay and tidal disruption could play out repeatedly over hundreds of billions of years, as each remaining world in turn spirals inward and meets its fate. The white dwarf would gradually consume its remaining children, growing slightly more massive with each meal while simultaneously growing dimmer and cooler as it radiates away its thermal energy. In this far future epoch, the night sky would be a vastly different place than anything we can imagine today. The familiar constellations would have long since drifted apart as individual stars followed their own paths through the galaxy. New stars would have formed and died, some exploding as supernovae and others quietly fading to white dwarfs like our own sun. The galaxy itself would have evolved, perhaps merging with Andromeda to create a new cosmic structure with its own unique architecture. Any remaining worlds in our solar system would witness these changes from a perspective of almost unimaginable loneliness. The warm, life-giving star that once illuminated their days would have become a fading ember, providing barely enough heat to keep hydrogen from freezing solid. The space between worlds would be darker and colder than the most remote regions of our current solar system. Yet even in this cosmic winter, there might be pockets of activity and change. Radioactive decay in planetary cores could still provide heat, potentially maintaining subsurface oceans on worlds with sufficient internal energy sources. The slow collision of asteroids and comets could still reshape surfaces and deliver new materials to airless worlds. The universe would not be static, merely operating at a pace that makes geological time seem frantic by comparison. The story of our solar system's death is ultimately a story about the nature of time itself and our place within the vast cosmic narrative. We exist during a brief, brilliant moment when the conditions are just right for complexity and consciousness to emerge. The sun shines steadily, the planets maintain stable orbits, and the chemistry of life unfolds in countless intricate ways across our small corner of the universe. But this moment, however precious, is temporary. The cosmic forces that created our solar system continue to operate, driving changes that will ultimately transform everything we know beyond recognition. It's a sobering reminder of our own mortality writ large across the cosmos. But it's also a testament to the incredible creativity of the universe, which finds ways to create beauty and meaning even in the face of inevitable change. As we contemplate these vast stretches of future time, we're reminded that the story of our solar system is still being written. The chapters we've explored tonight are predictions based on our current understanding of physics and astronomy, but the universe has a way of surprising us. New discoveries could reveal unexpected twists in the tale, forces we haven't yet imagined or possibilities we haven't yet considered. What remains constant is the sense of wonder that drives us to ask these questions in the first place. The same curiosity that led ancient astronomers to map the movements of planets across the night sky now propels us to peer billions of years into the future, imagining the ultimate fate of worlds we'll never see. In contemplating the death of our solar system, we're really exploring what it means to be part of something larger than ourselves, participants in a cosmic story that began long before we arrived and will continue long after we're gone. The contemplation of such vast timescales brings us face to face with one of the most profound questions in cosmology. What happens when the last star finally burns out? Our solar system's death, dramatic as it may be, represents just one small note in a much grander cosmic symphony that's slowly winding down towards silence. You see, star formation isn't an endless process. Throughout the universe, stars are being born in stellar nurseries where clouds of gas and dust collapse under their own gravity. But this cosmic recycling program has limits. Each generation of stars burns through hydrogen and creates heavier elements, but with every cycle, more and more material gets locked away in white dwarfs, neutron stars, and black holes. The universe is gradually running out of the raw materials needed to create new suns. Current estimates suggest that star formation will peak sometime in the next few billion years and then begin a long, slow decline. Within 100 billion years or so, the last new stars will flicker to life in the cold depths of space. After that, the universe will be left with whatever stellar remnants remain from this final generation, and the long twilight of the cosmos will truly begin. This has fascinating implications for any solar systems that might exist during those distant epochs. Imagine worlds orbiting the very last stars in the universe, their inhabitants watching as the galaxy around them gradually goes dark. One by one, the lights would go out as ancient red dwarfs finally exhaust their fuel and fade to brown dwarfs, then to cold, dark spheres of degenerate matter. Red dwarf stars, those dim, long-lived suns that make up the majority of stars in our galaxy, could potentially burn for trillions of years. They're the marathon runners of the stellar world, conserving their hydrogen fuel so efficiently that they could outlive virtually every other type of star by factors of hundreds or thousands. Any planets orbiting these stellar misers might witness the ultimate end of the age of stars, becoming the final outposts of warmth and light in an increasingly cold and empty universe. But even these stellar survivors face their own peculiar challenges. Red dwarfs are notorious for their violent mood swings, unleashing powerful flares that can strip away planetary atmospheres and sterilize surfaces with intense radiation. Any life that manages to evolve around these temperamental stars would need to be remarkably resilient, capable of surviving periodic bombardments that would make our worst solar storms look like gentle summer breezes. The physics of planetary evolution around such long-lived stars opens up intriguing possibilities that stretch our understanding of habitability. Worlds that start out frozen and lifeless might gradually warm up as their parent star settles into a more stable middle age. Conversely, planets that begin with thick atmospheres might see those protective blankets slowly eroded away by eons of stellar tantrums. There's something almost poetic about the idea that the last potentially habitable worlds in the universe might orbit these humble red dwarf suns. While massive, brilliant stars like our Sun live fast and die young in cosmic terms, these stellar wallflowers persist for so long that entire evolutionary sagas could unfold around them multiple times over. As we venture into these truly deep time scenarios, the very concept of planetary systems begins to evolve in unexpected ways. The gentle gravitational perturbations we discussed earlier, those stellar encounters that slowly reshape solar systems over billions of years, would have ample time to work their magic. Given enough time, even the most stable planetary configurations would eventually be disrupted. Computer simulations that follow these processes across hundreds of billions of years reveal a universe in constant, slow-motion flux. Planets migrate inward and outward, sometimes switching orbits with their neighbours in a cosmic game of musical chairs that plays out over timescales that dwarf the current age of the universe. Some worlds spiral into their parent stars, while others are flung outward into the cold depths of interstellar space. The survivors of these gravitational reshufflings would inhabit solar systems that bear little resemblance to the orderly arrangements we see today. Planets might follow highly elliptical orbits that carry them from scorching proximity to their star to frigid outer reaches where atmospheres freeze solid. Others might be locked in complex resonances, their orbital periods carefully synchronized by billions of years of gravitational fine-tuning. These dynamically evolved systems could harbor their own forms of exotic beauty. Imagine a world whose eccentric orbit carries it through dramatically different climate zones over the course of its year. During closest approach to its star, the planet might experience a brief, intense summer where ice caps melt and dormant life awakens. As it swings outward again, everything would gradually freeze, entering a long hibernation until the next orbital summer arrives. Such extreme seasonal variations might drive evolutionary adaptations unlike anything we see on Earth. Life forms might develop the ability to remain dormant for thousands of years, awakening only during the brief windows when conditions become favorable. Entire ecosystems could evolve around these cycles of freeze and thaw, creating biological rhythms that span millennia rather than months. The asteroid belts and comet clouds of these ancient systems would tell their own stories of deep time. Countless impacts and near misses would gradually grind down rocky debris, creating vast fields of dust and pebbles that catch and scatter the fading light of dying stars. Some of this material might gradually coalesce into new small worlds, while other fragments would spiral inward to rain down on surviving planets in slow-motion meteor showers that could last for millions of years. The moons of gas giant planets face particularly complex fates during these extended evolutionary phases. Tidal heating from their massive parents could keep them warm long after their primary stars have cooled beyond the point of providing meaningful heat. Europa-like worlds might maintain subsurface oceans for trillions of years, creating isolated biospheres that evolve in complete independence from the larger universe around them. These hidden ocean worlds represent perhaps the most intriguing possibility for life's persistence in the far future cosmos. Protected from the harsh radiation environment of space by kilometers of ice and warmed by the steady flexing of tidal forces, they could serve as cosmic arcs, preserving the spark of biology long after surface conditions become hostile to life. The chemistry of these isolated oceans would gradually evolve in fascinating ways. Cut off from the surface world and its supply of fresh materials, life in these hidden seas would need to become incredibly efficient at recycling nutrients and energy. Over geological time, entire ecosystems might evolve that are completely self-contained, requiring nothing from the outside universe except the gentle, tidal heating that keeps their world liquid. Some scientists speculate that such systems might develop their own forms of intelligence, consciousness that evolves in the eternal darkness beneath ice shells, completely unaware of the stars and galaxies beyond their frozen ceiling. These beings would inhabit a universe consisting entirely of their ocean world, developing science and philosophy based on water currents, temperature gradients, and the subtle vibrations that propagate through their liquid domain. The possibility of intelligence emerging in such isolated environments raises profound questions about the nature of consciousness and its relationship to the cosmos. Would minds that evolved in complete darkness develop concepts equivalent to our notions of light and vision? How would they understand space and time without access to astronomical observations? Their entire cosmology would be built around the physics of their ocean world, creating ways of understanding reality that might be completely alien to our surface-dwelling perspective. As stellar evolution continues its inexorable march toward cooler, dimmer endpoints, these hidden biospheres might become the dominant form of complex organization in the universe. While the surfaces of worlds grow cold and lifeless, vast networks of subsurface ecosystems could flourish in the gentle warmth of tidal heating, creating a shadow biosphere that persists long after the age of surface life has ended. The timescales involved in these scenarios stretch our comprehension to its limits. We're discussing epochs that are not just longer than human history, but longer than the entire evolutionary history of complex life on Earth by factors of millions. During such periods, the very nature of matter itself might undergo changes that we can barely imagine. Quantum mechanics tells us that even the most stable atomic nuclei have finite lifetimes when viewed across truly cosmic timescales. Protons, the building blocks of ordinary matter, might eventually decay into lighter particles and energy. If this process occurs, it would represent the ultimate end of chemistry as we know it, as atoms themselves would gradually disintegrate over periods measured in numbers so large they require exponential notation just to write down. The prospect of proton decay introduces a kind of cosmic mortality that applies not just to stars and planets, but to matter itself. Even if some form of intelligence manages to survive the death of stars and the cooling of the universe, it would eventually face the gradual dissolution of the very atoms that compose it. This represents perhaps the most fundamental limit to the persistence of complexity in our universe. Yet, even in contemplating such ultimate endings, there's room for speculation about forms of organization that might transcend our current understanding of life and intelligence. Perhaps consciousness could find ways to encode itself in the patterns of quantum fields, persisting even as ordinary matter dissolves. Or maybe intelligence could learn to harness the energy released by proton decay itself, finding ways to extract meaning and purpose from the universe's final exhalation. These ideas venture far beyond the realm of established science into the territory of informed speculation, but they represent humanity's deepest attempt to understand our place in the cosmic story. By following the threads of physics and astronomy to their logical conclusions, we're exploring not just the fate of our solar system, but the ultimate destiny of everything that exists. The journey we've taken tonight, from the gradual brightening of our sun to the speculative far future of proton decay, represents one of the most ambitious intellectual adventures our species has ever undertaken. We're using the tools of science to peer across temporal chasms so vast that they make the age of the universe itself seem like a brief moment. In doing so, we've discovered that the cosmos is not a static stage upon which the drama of existence unfolds, but rather a dynamic, evolving entity that carries within itself the seeds of both creation and destruction. Our solar system, for all its apparent permanence, is merely one temporary arrangement in an ongoing cosmic dance that began with a Big Bang and will continue until the last black holes evaporate in the unimaginably distant future. There's something both humbling and inspiring about this perspective. Humbling because it reminds us of our own cosmic insignificance, the fleeting nature of not just human civilization, but of the very worlds and stars that seem so permanent from our earthbound perspective. Yet it's also inspiring because it reveals the incredible creativity and resilience of the universe, which finds ways to create beauty, complexity, and meaning even in the face of inevitable change. As we drift toward the conclusion of our cosmic journey, it's worth reflecting on why we undertake such explorations in the first place. The death of our solar system is not something any human will ever witness directly. The timescales involved are so vast that they transcend not just individual human experience, but the entire span of our species' existence by factors that strain comprehension. Yet there's value in stretching our minds to encompass these cosmic perspectives. In contemplating the ultimate fate of our solar system, we gain a deeper appreciation for the remarkable circumstances that allow us to exist at all. We live during a brief, precious interval when the conditions are just right for life, consciousness, and wonder to flourish in our corner of the universe. This cosmic perspective doesn't diminish the importance of our daily lives or the challenges we face as a species. If anything, it enhances them by placing them within a larger context of meaning and purpose. We are the universe becoming aware of itself, matter organized in such a way that it can contemplate its own origins and destiny. The questions we've explored tonight about stellar evolution and planetary dynamics, about the persistence of life and the nature of deep time, are really questions about ourselves and our place in the grand cosmic story. By understanding how our solar system will end, we better understand how precious and remarkable it is that we're here to ask such questions at all. The story of our solar system's death is ultimately a meditation on the nature of impermanence itself. Every sunrise we witness, every orbit our planet completes around its parent star, every breath we take exists within this vast cosmic context of inevitable change. Yet rather than rendering our existence meaningless, this knowledge somehow makes each moment more precious, more worthy of attention and care. Think about it for a moment. You woke up this morning on a world that's been circling the same star for over 4 billion years, part of a cosmic dance that began long before life itself emerged from the primordial seas. The very atoms in your body were forged in the nuclear furnaces of ancient stars that lived and died before our sun was even born. You are quite literally made of star stuff, temporary arrangements of cosmic material that have somehow achieved the extraordinary ability to contemplate the universe that created them. This perspective transforms how we might view the challenges and opportunities of our current moment in cosmic history. We exist during what astronomers sometimes call the stelliferous era, the age of stars when nuclear fusion lights up the cosmos and provides the energy necessary for complexity and life to flourish. This era, which began shortly after the Big Bang and will continue for trillions of years to come, represents just one chapter in the universe's much longer story. Before stars, there was only the cosmic dark age, a period when the universe was filled with hydrogen and helium, but no sources of light beyond the fading afterglow of creation itself. After stars, there will come the degenerate era, when stellar remnants like white dwarfs and neutron stars dominate the cosmic landscape. And beyond that, epochs so distant and strange that we can barely imagine them, when even black holes evaporate and the universe settles into its final state of maximum entropy. We live during the universe's most creative and energetic period, when stars are born in stellar nurseries, when planets coalesce from cosmic dust, when chemistry becomes complex enough to support the intricate molecular dances we call life. In a very real sense, we are witnesses to the universe at its most magnificent, most vibrant, most alive. The gradual changes we've explored tonight, from the brightening of our sun to the eventual dispersal of planets by passing stars, occur against this backdrop of cosmic creativity. While our particular solar system faces inevitable transformation, the universe continues to birth new stellar systems, new worlds, new opportunities for complexity and perhaps consciousness to emerge. Current observations suggest there may be more potentially habitable worlds in our galaxy than there are grains of sand on all the beaches of Earth. Each of these worlds tells its own story of cosmic evolution, facing its own unique challenges and opportunities as its parent star ages and changes. Some orbit ancient red dwarf stars that will burn for trillions of years, offering unprecedented stability for evolutionary processes to unfold. Others circle young hot stars that burn brightly but briefly, creating intense but fleeting opportunities for life to emerge and flourish. The diversity of these planetary systems stretches our imagination and challenges our assumptions about what constitutes a habitable world. Some planets might be tidally locked to their stars, with permanent day and night sides creating unique climate patterns unlike anything we see on Earth. Others might follow highly elliptical orbits that produce extreme seasonal variations spanning decades or centuries. There could be ocean worlds completely covered in liquid water, with no land masses at all, where life evolves in three-dimensional aquatic environments of incredible complexity. Desert worlds might harbour life forms that extract moisture from the atmosphere itself, creating ecosystems based on entirely different biochemical foundations than those we're familiar with. The moons of gas giant planets offer their own intriguing possibilities, warmed by tidal heating rather than stellar radiation, maintaining liquid oceans beneath protective shells of ice. These hidden biospheres could persist long after their parent stars have evolved beyond the ability to support surface life, creating cosmic refugees where biological complexity continues to flourish in the darkness. As we contemplate these possibilities, we're reminded that the death of our particular solar system doesn't represent the end of the cosmic story, but merely one transition in an ongoing narrative of transformation and renewal. The heavy elements forged in our sun's core over billions of years will eventually be scattered into space, becoming the raw materials for future generations of stars and planets. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements will continue their cosmic journey long after our solar system has ceased to exist. They'll be incorporated into new worlds, perhaps becoming part of entirely different forms of life that we can't even imagine. In a very real sense, we are participating in a cosmic recycling program that connects us to both the deep past and the distant future. This perspective offers a kind of secular immortality, the recognition that while our individual lives and even our entire species may be temporary, we're part of something larger and more enduring. The atoms that comprise us have existed since shortly after the Big Bang and will continue to exist until the universe itself reaches its final state. We are temporary arrangements of eternal material, brief patterns in the cosmic dance of matter and energy. The knowledge we've gained about stellar evolution and planetary dynamics, about the life cycles of stars and the fate of worlds, represents one of humanity's greatest intellectual achievements. Through careful observation, mathematical modelling, and scientific reasoning, we've managed to peer across vast gulfs of space and time to understand processes that unfold over billions of years. This understanding doesn't just satisfy our curiosity about the cosmos, it also provides practical insights that could prove crucial for our species' long-term survival. By studying how other solar systems evolve and change, we're learning about the challenges and opportunities that await us in our own cosmic future. This knowledge could inform decisions about space exploration, planetary protection, and even the possibility of finding new homes among the stars. The technologies we develop to study distant worlds and ancient light also drive innovations that benefit life here on Earth. The same instruments that detect exoplanets orbiting other stars help us monitor our own planet's climate and atmospheric composition. The mathematical techniques used to model stellar evolution find applications in everything from weather prediction to financial analysis. Perhaps most importantly, the cosmic perspective we gain from studying the death of solar systems helps us appreciate the profound interconnectedness of all things. The boundaries we draw between self and other, between Earth and space, between present and future, begin to dissolve when we view ourselves as part of an ongoing cosmic story that spans billions of years and countless worlds. This doesn't diminish the importance of our immediate concerns and responsibilities. If anything, it enhances them by placing them within a larger context of meaning and purpose. We are the universe's way of understanding itself, matter organized in such a way that it can contemplate its own nature and destiny. The questions we ask about stellar death and planetary evolution are really questions about our own origins and future. In the end, the story of our solar system's death is also the story of its ongoing transformation. While the particular arrangement of worlds and orbits we call home will eventually change beyond recognition, the underlying creative process of the universe continue unabated. New stars are born, new planets form, new opportunities for complexity and consciousness emerge from the cosmic dance of matter and energy. We are privileged to exist during a time when we can understand these processes and our place within them. The same curiosity that drives us to explore the far future of our solar system also motivates us to search for life beyond Earth, to develop technologies that could ensure our species' long-term survival, and to create art, music, and literature that captures the wonder and beauty of our cosmic situation. This awareness of our cosmic context brings with it both profound responsibility and extraordinary opportunity. We stand at a unique moment in the universe's history, equipped with the tools to understand our place within it, and perhaps even to influence our cosmic destiny. The knowledge we've gained about stellar evolution and planetary dynamics opens up possibilities that would have seemed like pure fantasy just a few generations ago. Consider the prospect of becoming a multi-planetary species, spreading life beyond Earth before our Sun begins its final transformations. The same understanding that allows us to predict the death of our solar system also guides our search for potentially habitable worlds around other stars. We're learning to identify the signatures of distant atmospheres, to detect the presence of water and organic compounds across interstellar distances, to recognize the conditions that might support life as we know it. The engineering challenges involved in such endeavors are staggering, but they're not insurmountable, given sufficient time and determination. We're talking about timescales that dwarf human civilization, periods that offer countless opportunities for technological advancement and cosmic exploration. The species that eventually witnesses the sun's transformation into a red giant may bear little resemblance to us today, having evolved not just biologically, but technologically into something we can barely imagine. Yet even if we never venture beyond our solar system, even if we remain bound to these familiar worlds throughout our species' existence, we can take comfort in knowing that our atoms will continue their cosmic journey. The elements that make up our bodies, our cities, our entire world will someday be scattered among the stars, becoming part of new stories we'll never witness but somehow helped to write. The universe has a way of preserving what matters most: information, patterns, the complex arrangements that give rise to beauty and meaning. These find ways to persist even as their physical substrates change and evolve. The knowledge we've gained about our cosmic situation, the art we've created in response to it, the love and wonder we've felt while contemplating the stars. These contributions to the universe's growing self-awareness may prove more enduring than any physical monument we could construct. So, as we reach the end of our journey tonight, as we return from these vast contemplations of deep time to the familiar rhythms of our daily lives, let's carry with us a sense of both humility and purpose. We are temporary arrangements of star stuff, brief patterns in the cosmic dance, but we are also the universe's way of understanding itself. In studying the death of our solar system, we've really been exploring the nature of impermanence and our own remarkable place within the grand story of existence. The next time you look up at the night sky, remember that you're seeing light that has travelled across vast distances and spans of time to reach you. Those stars are telling stories of nuclear fusion and gravitational collapse, of planets forming and atmospheres evolving, of the same cosmic processes that will eventually transform our own solar system beyond recognition. You are part of that story, connected to every star and planet through the shared history of atoms and energy that makes up everything we know. Sleep well tonight, fellow travellers, knowing that you exist during one of the universe's most creative and vibrant epochs, when stars shine and planets dance and consciousness has emerged to contemplate it all. Tomorrow brings new opportunities to explore, to understand, to create meaning from the cosmic materials we've inherited from ancient stars. The story continues, and you're part of writing it. It continues, and you're part of writing it.